Okay, what we're going to be centering on today is spectroscopy. Spectroscopy is probably the most used instrument in science, and it's probably the least taught instrument in our educational system for whatever reason. Relatively simple instrument, and the principles are relatively simple. So people are learning around the world, and if you go on YouTube, you'll find lots of material for the educational world there. And they are making them out of toilet paper rolls, they're making them out of towel rolls. However, that's good for elementary school, lower elementary, but if you're a STEM student or a STEM teacher, to me you should be 3D printing them. So it's relatively easy with Tinkercad to make a circle, a square, or anything. So what is spectroscopy? So we've got light coming from the sun, okay? And then we make artificial light. So basically, we've gone over a lot of this, probably not so much you were here, but Elisa has gone through several parts of these principles we're going to talk about today. Is white light. White light is all colors put together. Then you have black light, which is black. Well, in the world of science, they want something called a black body. A black body it absorbs all light. So we're not going to talk a lot about it, but you have to understand that we've got a range of whatever you want. You can have a range of 0 to 100, or you can have a range on the computer, 0 to 255, and that's what we've worked on before. And then change those digitally, analog, and so on. So anyway, you have condensing light there. And during this summer, what we're going to talk about now, and Harker Heights Library done this at the very elementary level. This week, one of the science teachers there gave a presentation on refractor. And next week, or next time she gives it, it's going to be reflection. So these are the things that we can do with that light from the sun, from any light bulb, or from any light source. That's something that's really hot, metal, that's molten, and it puts out a certain light. Then we want to do things with it. In this case, you'll see up there, we want to diffract that light, okay? So what we're working on and talking about is diffraction. Reflection, refraction, and diffraction. So spectroscopy depends on diffraction. Okay. So we're going to go over the principles of it and why it's so important. So that light there, when it goes through a prism, now draw a medium-sized convex lens. Not concave, convex. Okay, you can see what we're doing with the light to start the basic thing, a learning process, and doing is we're using a prism. It just so happens when you put light into a prism, prism is going to diffract that light based on scientific principles. So almost all of us use lenses for something else. Glasses, telescopes, microscopes, most of them that we use are convex, like this. You can also have a concave. So in the world of astronomy, we've already gone through a fair amount of that, is if you use a convex lens, which is what Galileo used, it's long because it has to match the focal length of the lens and the wavelength of the light. Therefore, these telescopes get very, very long. So you don't want to say lay down at a night with a telescope that's 6 foot long and look up at the stars. Plus, modern day mounts for telescopes, generally speaking, won't handle it or won't do it very well. So what they've learned to do is to cut that light in half with a mirror. So this is where a mirror comes in. So the telescopes that have mirrors and that are short, like the one sitting next to you there, is a, we call them refractors, okay, and then reflectors, because that's light's bouncing off mirrors back and forth. So instead of being this long, now it's this long. So now you can tip it however you want on a mount. Plus it's lightweight. So, but once you have that, then you want to separate the light out into at least RGB, red, green, blue. And that's what she's got out there. So now at the top of it, your lens, draw a line and get a prism at the top. Just draw a line. The top of it is a prism and the bottom of it is a prism. So draw a line like that.
So separate.
And down here, draw another line.
Like this?
I think try to make a triangle out of that.
Oh.
I think that's what he's saying.
No, in the lens.
Inside
You're
the
going to
lens.
cut that lens up in parts.
Yeah, make a triangle on top and a triangle on bottom.
Just put a line in the middle.
Well, okay, sure.
Yeah, that's good.
That works.
That's one now. Put another line there and one line there. There you go. Now what we've done, the first step in this process, learning to manipulate light and sound, by the way. Sound and light are just waveforms and they're more or less the same. Is at the top and at the bottom you have a prism. So when we put a light through there, which she's got, if you look at it going through the center, that light is not changed. It goes through there. But on the ends of the prism, it will be diffracted into RGB or into the spectrum. Okay, that's the first principle we've got. So what we're talking about learning in the world of academics is light rays. You have a little light we'll be working with later that has 3 lights in it. Center light, one here like she's got, and one there. And want to put it through here, one here, and then we'll see what you're going to do with that light. That light will separate it out, but the middle, it will not. Okay, so put that under that. That's the electromagnetic spectrum. Electromagnetic spectrum is the world. It is the universe. Okay, so it starts down at the bottom with sound, and then it works up. Yeah, don't draw it. Wait, I'll tell you what part of it. We're not going to look at all of it. Not working on sound today, okay? And we're not working on long waves, radio waves. What we're working on is the visible spectrum, VAIOUS frequently, and the bottom end of the visible spectrum is red, infrared, IR. On top, as you go into the high energy, you got ultraviolet. So most people are familiar with ultraviolet because they get the black lights and they do funny things with them. They dance with them, they play games with them, and so on. So infrared they're not so familiar with, but they use it all the time. Every camera that you use, including every cell phone, now listen very close, has got an infrared filter in it, because an infrared goofs up our visible spectrum. So you don't know it, but there's a filter in there put in by the manufacturers. So in the world of science, you want that infrared. So it's divided into different parts. It's divided into near infrared, NIR, okay, far infrared. It's divided into at least 3 different parts for the world of science. Ultraviolet is the same thing. It's divided into A, B, and C. So A will go out there and get a suntan with maybe see, we probably should not look at it very long and not use it a whole lot. So it's getting into the dangerous high energy levels that will cause problems. So we know that too much sunburn, too much sun will cause skin cancer. So that's ultraviolet. And then we go up to the really high energy levels above there, which is X-ray. We all know about X-ray. Doctors use it all the time. And then gamma rays, which we hope we'll not get much of. So for some reason, the good Lord gave us our atmosphere that keep them out. If it came through, we'd probably all be dead. So, okay, so draw a spectrum there with RGB. Now this is the starting point. You do have to understand R is red, G is green, B is blue. Okay? But now we're getting into the wavelength. These are waveforms, and I forgot to bring it, but I have a slinky we use to teach this. The slinky can go this way, or it can go this way, or it can go circles. So these waves can go straight, they can go around in a circle, right hand or left hand, and you have to know how you want to handle that waveform. But the most important part is frequency, so write frequency. Now, this is where a lot of people get confused, because when they think about the spectrum, and people in science put it in books, it depends on which way they have it. If they have red here or red here. But it starts at 0, and then if it's red down at the bottom, then you know the ultraviolet is going to be here. So it's RGB. So where do you have red? Okay, so write red there. Okay, and then B for blue. So now, what you have to understand, as you go higher up, these waves are getting closer together. Okay, so the frequency is going higher, right? So your long waves are down at the radio end of it. So on that end, on the other side of red, put infrared, IR. Now we use infrared for our night vision. Okay, all of our night vision glasses, that's what they are. We cannot see infrared, but we have cameras and lenses and so on that can. So if we take the infrared filter out of any of our cameras, and what we'll be doing is the webcam for the inexpensive Spectrometer. You go in and you take out the infrared, and now you got a camera that will see a broader spectrum, and you can use it as a thermal camera or a night camera. So every camera's got that capability built in. It takes a little bit of work on people's parts to do it. So on this side here,
UV.
put ultraviolet. Okay. So now as we go forward, we're going to have to break that infrared down into different parts. The part that we want to use and the part that our hardcore astronomers use. Okay. So take this and just keep putting their number. So now it's a matter of what can we do with that wavelength. Draw a sine wave first so they see a sine wave. Okay. Now start near the edge of the paper and start another one overlapping them. So this is what we see in RGB. Red, green, blue. And there's many other colors, but we're just going to zero in on the easier ones. So most of you know that in the world of that we live in, you have two kinds of print or of colors. You have this kind of color, which is subtractive colors, cyan, magenta, and yellow. Okay? They're called subtractive colors. Then you have this kind of color, or that, display, where it's coming to you as a light. They call it display. That's RGB. So you do have to start putting some brain power on top of this to kind of, when you buy for your printer, when you go in the store, you can buy cyan, magenta, and yellow. It's not RGB. So you do kind of have to know that. So what we've got now is first of all, if you on the convex lens, what they do is they take out all of that part except for the top and the bottom. Okay? It doesn't do anything. So it's just wasted thing for the world of science. It's not for your eyeballs, but it is for that. Because your eyeballs, you want things to come in. You don't want them to get fuzzy and halos and so on. So anyway, what you want to do scientifically, you want to study red, you want to study green, you want to study blue. That's where diffraction comes in. So write down diffraction, D-I. Now remember we talked about reflection, okay, refraction, and this is diffraction. Now draw a line with this hole in it, or a slit, just a line. Look at the paper. So that can be anything. It can be just a sheet of plastic, a sheet of something or whatever, but it's got a slit in it. So now we're going to talk about a little bit on photography, I guess. Most of us have heard about or had contact with a pinhole camera. Well, pinhole takes out a lot of stuff, so you only have a little tiny bit coming through because your sensor or your eyeball can't handle it. Eyeball does, but the more you get to a camera that's got a little sensor, it can't handle that much like the eyeball can. So you need good lenses to manipulate it. In this case, now on this, a line down, did you draw it? Here. Draw a line down and all those little prisms. Anyway, just a line down. Yeah. A straight line down. I'm trying to find something to demo here if I can. Yeah, I'm not going to find it. I have one here. Now on that line, like the sheet I gave you, draw lots of little prisms. Prism, 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 prism. You see it?
No, I don't.
Okay, now do it on the other side too. Down at the bottom, do it on the other side. No, on the other side of your line. Okay, that's the first real advancement in a science of lenses. What we've done is taken the end of a convex lens, which are prisms, and got rid of all that wasted glass there, and now we put in that and made our lens, and it's called a Fresnel lens, F-E-S-N-E-L, Fresnel. Fresnel lens, the first use of it was in lighthouses. They give a better light and they throw it further. So they use this lens like this, where all those prisms work for you now, whereas in the lens up above, all that fat part of it is wasted, okay? It is not efficient. It can be used, it will work, but basically it's not going to do the work that you want it to do in science. So now if we put a hole there, put another line down there, it's called a slit. Same thing down here, and these have to be present with a slit. So now your pinhole camera has become a slit. Okay, now put light through the top slit. That's white light going through, but as it comes out, it's going to be diffracted and it's going to come out RGB. So now we've done something with the light, okay? So now what we can do is take a webcam, take the IR filter out or leave it in. It doesn't really matter a whole lot depending on what you want to do. And we can separate out the red, the green, and the blue. Okay? And this allows us to do certain things. The stars that we look at start out as a very hot star. Now, this has been around for years, so it's one of the mnemonics that I teach and has been taught, not by me, but by the educational world for at least 50 years. Is starts with O, okay? O, be a good girl and kiss me. Or good boy and kiss me. So O are the hot stars, the young ones, okay, okay. As you get down at the bottom, me, okay, kiss me, you've got the old stars, they're big and they're gonna die. Just like people, the older they get, the fatter they get. So these stars get old and then they blow up. And now you got a supernova or something else, it's no longer a star. Betelgeuse, if you've heard of that one, it's in Orion, and it's an old one. So these tend to be red. The ones at the top, O, are hot, okay? So this is where the spectrum comes in. We tend to, if you know, do any photography or use lenses, an incandescent bulb is a reddish bulb. It's tungsten, like iron when it heats up, gets molten, and it's reddish, okay? The hotter it gets, the more white it's going to get. Like